record. Okay. Good morning. Let's see here. So last day we started talking about chi-squareds, which is if we have 3 or more categories that we want to compare, then we're going to have, we'll work with this made up example. So consider a bag of M&Ms, which have just 3 colors, just because I don't want to do a ton of math. And so blue, red, and green. And you have a random sample of 99 M&Ms. If the colors are evenly distributed, right? So that's going to be your expected distribution. How many of each color would you expect? Now, we're not always going to talk about an even distribution, but it's the easiest and kind of most intuitive place to start. And so then I would expect, right, if it's evenly distributed, I would expect those 99 to be spread evenly across the 3 groups. We're aware that if I got an actual bag of M&Ms, I would have some observed counts of each color, and I could count those. And of course, they should add to 99. And so I kind of introduced this second situation. We're going to focus on the first situation, right? Where we had, okay, 30 and 28 are less than 33, and then 41 is quite a bit more than 33. So we suspect that maybe something's going on. Maybe greens are more likely to happen, right? All we'll be able to say is that it's not an even distribution if we reject H0. Whereas here, these values seem to be just kind of hovering around what we would expect. And so I suspect that I wouldn't reject H0 in that scenario. Okay, so then we said there were some conditions that we talked about that I'm not going to bring in, but I'll mention here. We have to have independence within and across each of these groups. So the M&Ms have to be independent of each other. And if we're randomly sampling, then we can assume that that's true. The new condition for a chi-squared is that we have to have at least 5 expected counts in each category. And so in our case, we have 33, so that's fine, so that's satisfied. And so our chi-squared goodness of fit test, which is what we're doing, how well does the even distribution fit what we observed? So I'm just going to snag the question specific hypotheses. So step 1 is still to state the hypotheses. And I'm just going to negate this, right? We said, all right, our alternative hypothesis is just going to be the negation of the null hypothesis. So the observed distribution of M&M colors is not evenly distributed. And that's all we'll be able to conclude from this chi-squared test. Okay, and then it's kind of where we ended. I did show you the chi-squared test statistic, which is similar to the Z that we've been working with, right? It still looks at how far is my observed value from the expected value. And here I'm just going to give it to you, /us, do the test. Chi-squared is the sum of the observed minus the expected squared. Oh, bracket looks weird. Divided by the expected for each category. Now, I'm going to throw the subscripts on there, right? The indices from I = 1 to k. The observed count in the category I, which starts at 1 and goes through k, I, and I, right? But all this is saying, so these are optional and I tend to drop them just because they make things look more confusing than they are. And so all it says is that you're gonna do this calculation for each category and then add them up. In fact, Excel does this calculation for you. And so you don't really need to do it that often. But let's just do it once since we have a small number of categories. So here, it's gonna bump it up, but maybe not. Let's just focus on these guys. Copy. Paste. What this means is that this is the expected 1 is 33, expected 2 is 33. Need to see where that is. And expected 3 is 33. Observation 1 is 30. The observed count for 2 is 28 and 03 is 41. Okay. There. Looks like a 1 to 2. So what this looks like for our chi-squared calculation is the observed minus the expected. And so we have 30 minus 33 squared divided by 33. And then I want the sum of each of these, right? So 28 minus 33 squared. Notice that we're just seeing how far is the observed from the expected. And because I'm adding them, I have to make them positive somehow. And I want to amplify large differences. So that's where the square comes in. And then the expected is taking the place of the standard error. It's not the standard error, but it's taking its place. Pretty sure that this calculation can be done in Excel. This can be done using, well, just using the regular math functions. So you can set up a formula and just drag and do it relatively quickly in Excel. But there's also a chi-squared test function. And so using Excel, either, I call it by hand. It's not by hand when we set up the calculation kind of to do it where we tell it what to do. Or using, pretty sure it's chi-squared. So chi-squared dot test. And I'm pretty sure it takes the observed and the expected. Does anyone have Excel? Nice. So you give it your list of observed values and the list of expected values, and then it would return the chi-squared test statistic. I'd probably set up my Excel sheet like something like this. Often I would have my observed column first and then my expected column, just because that's how we read it. I tried to enter it. Blue, red, green, and then 30, 28, and 41 for the observed. Yeah, and then 41. Yeah, I think it's chi-squared dot test.
Actual range.
Yep, so that's the observed. Oh, sorry, I'll change that to actual. Or here. 0.252. Okay. Well, let's see. Where's my, there. I'll just do it real quick here in this calculator, clear all. I want 30 minus 33 squared, then divided by 33 plus 28 minus 33 squared divided by 33 plus 40.
Does that mean that's the chances of?
So that's gonna tell you, oh, weird, I get something different, 2.97. Can I see what, what it looked
I have
like?
also got the same 2.9696. That's correct. That's correct.
Oh, switcheroos.
Gotcha.
Yeah.
Actual range.
Mm-hmm. Wait. I'm going to snag this. Did it change it?
Yeah, it did change it.
And is it?
It's not that.
Uh-oh.
0.226 if you read it.
Did I enter something wrong?
Doesn't look like it.
30, 28, 41. Oh, maybe it. Oh, does it spit out the p-value right away? Maybe.
Here it says chi-squared.test returns the test for independence. The value from chi-squared distribution for the statistic and the appropriate degrees of freedom.
Because we're not doing a test of independence.
What are we doing?
We're doing a goodness of fit test. That's okay. I'll have to play around with that. But our chi-squared is going to be 2.97. And that's our test statistic. I wonder if this is giving the tail area. So the thing about the chi-squared is that it's going to have degrees of freedom. You guys worked with degrees of freedom before? Does that sound familiar? No? Okay, so degrees of freedom means that the shape of the distribution is going to change depending on some value. And so for the chi-squared, the shape of the distribution depends on how many categories you have, right? And so the shape, I'll write that down. The shape of the chi-squared distribution depends on the degrees of freedom. Depends on the degrees of freedom. And so the degrees of freedom, which we abbreviate DF, is going to be K minus 1, where K, remember, is the number of categories, or maybe I haven't K, or maybe I'll say where K is the number of categories. So for us, we have 3 categories, red, blue, green, or whatever it was. And so we have 2 degrees of freedom. Now, in general, if we have 1 degree of freedom, the distribution looks like this. So if the degrees of freedom is 1, if we have 2 degrees of freedom, then it starts to kind of even out like this. Degrees of freedom equals 2. And then 3 degrees of freedom, it starts to kind of, and I might be exaggerating a little bit, how quickly it moves. Sorry, this should be, bless you. But it starts to approach this kind of normal distribution-ish as you increase the number of categories. And so here, what's kind of fun about the chi-squared is that it's all going to be up against 0. And so we're used to this symmetric distribution of Z where we can have negative values, positive values, and it behaves the same by symmetry around 0. And so we're not going to have that anymore for chi-squareds. And so the chi-squared that we found, 2.97, right, is going to be somewhere on this axis here, right? And so depending on our degrees of freedom, which in our case we have 2, right, then our chi-squared of 2.97, let's say, is going to be out here somewhere. Now for our chi-squared, the p-value is going to be the area in the upper tail because there is no tail on the lower end. So for chi-squared, the p-value is the area in the upper tail. What's nice is we don't have to worry about one-sided or two-sided tests because we just said, well, our alternative hypothesis, we just negate the null hypothesis, and that's our alternative. And then our p-value is just going to be the area in the tail here. Now this part, I'm more confident in Excel because of course Excel can give us this p-value, this area in the tail. So we need to calculate the chi-squared, and it sounds to me like we have to do it by hand. I think I need to. Yeah, because it should be 2.97. So you have to set up this calculation.
Yeah.
And then here, I'll just make a note, might not work for a goodness of fit test. That's more of a note for me to look into. I just assumed that it would be able to take any actual unexpected, but maybe that's my bad. But this calculation is why I only wanted 3 categories. Of course, we can have more categories, especially if we're adding these up in Excel, but
Here it says the test. Yeah, it says use chi-squared test. Returns the p-value.
oh, okay, cool. So maybe I'll make it in pink so it's happy. P-value. We'll check that. Yeah, so we'll confirm that. It's all part of it. So the chi-squared, so the p-value is the area in the upper tail. Now this one is the one that I'm more confident in. We can use chi-squared dot dist. And I think it takes the value, so the chi-squared value, probably the degrees of freedom. Are you able to?
return to left tail probability. Squared.
And are these the arguments it wants?
Next, degree of freedom. And
Oh, okay. And so we would want, oh, okay, but the x should be the chi-squared.
Yeah.
But I'll do x, but this is the chi-squared that we calculated. And then the cumulative will be true because we want the area up to and including that point. And so if we do, let's try this, chi-squared dot dist of well, ideally, if you're able to reference the cell where you got the 2.97-ish, that would be good. And we have 2 degrees of freedom and we want the cumulative. Should give the area to the left, I think it said, right?
yeah.
Does it return anything? Something like 0.7 something. Hopefully. Oh yeah, you bet.
Why is the degrees of freedom 2?
Because we have three categories. So k equals 3. So the degrees of freedom is k minus 1,
Right.
which makes 2. Good. Nice.
Yeah. And what's the degrees of freedom?
2.
0.77.
Cha-ching, 0.77
Yeah, 7,
or 3.
3, 4.
3, 4. Okay, so this, if we think about our chi-squared distribution, we gave it this value here. So this is at 0. This is 2.97-ish. So this area is the 0.773463. But we want this area, this is the p-value. So the p-value then is going to be 1 minus 0.773463. The area under the curve is always 1 because it's a probability. And so,
Which is our chi-squared.
awesome. And point, hopefully.
Gives us a percentage of the tail.
Yeah, so it just bypasses all the calculations and just gives you the p-value. Nice. Okay, so 0.252-ish.
0.226.
So the 0.77 is the chi-squared top?
This one, the
No,
2.
no, 0.77.
So this is going to be the area to the left of
It
the,
doesn't have a name?
no,
Okay. Area
Yeah.
to the left.
yeah, it's just the area to the left. So it's the probability of seeing something less than that. But we're always interested in seeing the probability of seeing something more than what we saw. And that's our p-value. So it's like a gateway to the p-value. Yeah. I'm surprised that this one isn't. Wasn't this one 0.252? Why are they so different?
The 252 was what I originally calculated when I did expected and then observed.
Oh, and then what does this do if you swap them?
So that's what it was, that's why I did swap them afterwards.
You had them in the wrong order
When you
before to get that 0.25.
And is
And then you
this
switched the order to the other way, you got the 0.2.
0.226, probably
Yeah, the
something?
0.252 that I got was when I put the expected first, observed second.
And what should it be?
0.2265. Exactly what we got down below.
Oh, phew. Had me worried. I was
Yeah,
going
so
for
it's just-
0.252.
It's just that number there. That was,
Whew. Okay, so that's kind of fun. So the chi-squared test bypasses 2 steps, right?
not to set up the equation.
You don't have to do that. You don't have to do this calculation, and it knows your degrees of freedom, and it knows that you don't want the area to the left. You actually want the area to the right, and so that's going to save you some time, I think. You can do it by hand, but why?
Are we always trying to find p-value?
Yes. Yeah. Yeah, because we use the p-value to draw our conclusion, right? And so if the p-value is small enough, right, then we have enough evidence to reject H naught. Right? In this case, it's not small enough. So maybe where is I'll write step 3 up here. I kind of got carried away. Step 3 is find the p-value. But I'll also make a note here, maybe in green. Notice the chi-squared dot test function skips the chi-squared calculation, finding the degrees of freedom, and finding the area to the left. Kind of a valuable player there. So for our conclusion, which is our step 4, if the p-value is small enough. Now let's remember what the p-value is, because I do find traditionally when I teach this stuff, everyone kind of understands that, okay, the p-values, it's important, clearly, she says it a lot, but what is it? And so you have this understanding that, okay, it's important, clearly, but what is it? And unfortunately, all I can do, well, I can give you the Snoop Dogg meme. That's about it. But all I can do is just give you the definition of the p-value, which is it's the probability, which means an area under the curve, right, of seeing something as extreme or more extreme, right? And so that's going to be an area in the tail, right? Regardless of if it's a Z distribution or a chi-squared, or later a T distribution, right? So regardless of the distribution, it's the area in the tail. That's the probability of seeing something as extreme or more extreme, assuming the null hypothesis is true. And so if the probability that the null hypothesis is true, basically, is small, then you say, okay, fine, it could have happened with some probability, right? Some very small probability, but it's unlikely to have happened just by chance alone. And so that's when we reject H naught in favor of HA. There's a chance that we're wrong, and we talked about decision errors, right? And so then there's a chance that I'm making a type 1 error, but I am relying on these probabilities, right? And so there's always a chance that we're wrong, but based on the probabilities. And so here, I'll write down again, the p-value is the probability, which means it's an area under the curve. What's nice is any curve. The area under the probability of seeing something, and by something I mean a test statistic of seeing something as extreme, oops, or more extreme. This makes it the area in the tails, potentially both tails if you're in a Z, the area in the tails. And that also depends on your alternative. If we think back to 1 or 2 sample proportions, we had 1 or 2-sided tests. The default is a 2-sided test, so then it's the area in 2 tails, right? So of seeing something as extreme or more extreme than what we saw, assuming H naught is true. Oops, make that look like true. This part is what we're hinging it on, right? We did all our testing assuming the null hypothesis was true, and then we see something kind of more extreme than what we would expect by chance. And so here, if the probability, which is the p-value, is small, that's evidence against H naught. That is evidence against H naught. Oops. So if the p-value is small enough, right, less than 0.05, so many less than alpha equal to 0.05, right, then you have enough evidence to reject H naught. Okay. I'll confess that my first stats course that I ever took, it wasn't until I was studying for the final exam that it clicked what the p-value actually was. So that's why I think that's totally normal to have this kind of, okay, that's totally fine. It's just going to be one of those things that if you work with it enough, eventually it will click, but you just have to be patient. And so that's why I bring it up now, because I feel like it's totally normal to feel like, okay, I get that it's important, okay? And you can kind of, okay, I get that, and you can memorize rules and stuff, but it's going to just take some time to sink in, and you'll get there. And
Third value be?
yeah, it's basically how in our case, it's going to be the probability that these observed counts actually follow a normal distribution, or an even distribution, right? So it's not technically correct, but it is helpful to think of the p-value as the probability that the null hypothesis is true. So I'll write that down, but just be aware that it is helpful to think of the p-value as the probability that H naught is true, that at least will get you to, okay, then I need some threshold where if it's smaller than 0.05, then I don't feel comfortable saying that H naught is true anymore. So then I'm going to reject it, right? So not technically correct, but close enough, right? Especially for our purposes. So the p-value, you can think of it as the probability that H naught is true. And so for a good long while, right, we're going to say that, right, we start and we assume that the observed distribution of M&M colors is evenly distributed until we have evidence otherwise, right? But so you're going to hang out here in H naught until you have a test statistic that puts you far enough into the tail, right? Then you reject H naught in favor of HA. But so your default is H naught until you have evidence against it. Okay? And the probability that H naught is true has to be less than 5% or 0.05 in order to move to HA. Okay. Kind of difficult concepts, I know. So our conclusion, we have a p-value. We found it was 0.2265. So since our p-value of 0.2265, right, we know what it is, and so just say what it is. What do we have to do? We have to compare it to 0.05. Is this less than 0.05 or not? It's not less than 0.05, and so it is not less than 0.05. And maybe I'll say alpha equals 0.05 because alpha is our significance level. So we do not have enough evidence to reject H naught. So we do not have enough evidence to reject H naught. This is the same conclusion or the same setup that we were using before, right? We say what our p-value is, how does it compare to 0.05, and then what do you do with your H naught? You either have enough evidence to reject it or you do not, right? And so in this case, it's not less than 0.05, so we do not have enough evidence to reject H naught, right? And so what does that mean in terms of the question? It means that the distribution of M&M colors is evenly distributed. Or how did I write my null hypothesis? The observed distribution of M&M colors. Maybe I'll just write it out. Therefore, the M&M colors are evenly distributed. Oops. Right, so I'm going to break this down into 3 parts again, right? Part 1 of your conclusion is you compare your p-value, compare the p-value to the alpha level. Second part of the conclusion is you either have enough evidence to reject H naught or you do not have enough evidence to reject H naught. And the reason we're doing our conclusion in terms of H naught is because we set out assuming that it was true until I was able to find evidence otherwise. And so you don't bring in the alternative hypothesis unless you reject H naught. Then you can say, okay, then I reject it. Well, in favor of what? In favor of the alternative. Okay, so a lot of people want to talk in terms of the alternative hypothesis, but really we should be doing our conclusion in terms of H naught. And so sure. The conclusion in terms of H naught. And what I mean there is you either have enough evidence to reject H naught, or I'll just copy this sneakily, or you do not have enough evidence to reject H naught. Those are your only two options, right? And how do you get there? If the p-value is less than 0.05, you have enough evidence to reject H naught, and if the p-value is greater than 0.05, then you do not have enough evidence to reject H naught. This is where, if you're rejecting H naught, you're allowed to say, you can just end the sentence if it makes it cleaner for you, because then they're exactly the same, right? Just the negation. But if you're rejecting it, you can say in favor of HA. But you don't have to. That's going to come with time, I think. Or I know. And then finally, what does that mean in terms of the question? Right. We have to talk about our M&Ms. The colors are evenly distributed. So then the third part of the conclusion is the conclusion in terms of the question. Right. Okay. Good. Usually I don't have time to do a test of independence, but if you have two categorical variables with two or more categories each, right? Then you could have this two-way table, it's called, and you can test for independence. And so that's what I thought that chi-square test was doing. Now, I'm just going to introduce it. And so maybe, well, this is a new page, I guess. We can analyze, well, I guess any questions about that one? I'm just assuming that you'll jump in if you have a question. Fair assumption, I hope. So we can analyze two categorical variables, and we can analyze whether two categorical variables are independent of each other. Using a chi-squared test of independence. So just like Z was used for a one sample proportion and a two sample proportion scenario, chi-squared is multi-purpose as well. So, but the same idea. So how you calculate the test statistics stays the same, and how you find the p-value stays the same. It's just the degrees of freedom and how you find the expected counts that changes. And so Two categorical variables are independent to each other using a chi-squared test of independence. So what this is going to look like, maybe I'll highlight this name here. Is you would have maybe what could we do? We could look at the different brands of, I don't know, I guess M&M's only one brand. Maybe bought at different stores or something, right? Two categorical variables. Or maybe I should move away from the M&M's.
With peanuts or the chocolate stuff.
Hey, nice. Peanut M&Ms, or chocolate M&Ms. Is there a peanut butter M&M yet?
There is peanut butter.
Haha, peanut butter. Just to, oh. So we can really mess up these counts then. Yeah, it turns out they're just brown, yellow, and orange. Probably. Well, that's okay, actually. That's probably good. So here, M&M type, right, is a categorical variable with 3 categories. And let's say, was it blue, red, green? Right, M&M color is another categorical variable, right? And so what we can say is, okay, well, I can have a random sample of peanut M&Ms and I can find how many blues, reds, and greens there are. And I can have chocolate M&Ms and I can find how many blue, reds, and greens there are. And same thing with the peanut butter ones. And then I'm going to have row totals and column totals. Right, I'm gonna have some total number of peanut M&Ms, chocolate M&Ms, and peanut butter M&Ms, and they don't have to be the same. Often they are just for kind of simplicity in reporting, but they don't have to be. And then we have some total number of blue M&Ms, red M&Ms, and green M&Ms, and then some total number of M&Ms. So here, I don't want to make up numbers. Sure.
I think I can't remember correctly. It's a strange thing to say, but I'm pretty sure red is supposed to have twice as many in the bag.
Oh, really? Yeah.
I feel like I remember looking at that.
Very interesting. So then,
What got you to that point? That's what I'm interested in.
so someone's done the work already.
Yes.
Yeah. So you would have some counts here, right? So some number, blah, blah, blah. I can't make up numbers. It's too hard. Fine. 34, 18, and 30. Just throwing stuff out there.
I'm sorry, I had that wrong. The other way around.
Oh,
Blue is almost double the red.
okay, then 15. So let's do, you know what, let's go crazy. Let's go 6 here. And 14.
And then green is a little bit more than red.
Okay, thank you. This is good. I'm gonna go for 20 here. Let's go for,
This is roughly 56 per bag.
oh, so many parameters. I actually might get there.
and then Peanuts.
Oh, okay, well,
But the distribution is the same throughout all of them in general.
let's do 25. I'm just gonna grab my calculator and just quickly grab these totals. Okay. Oh, maybe. Yeah, did I get it or what? Oh, thank you. Down here? Yeah.
Peanut is 79.
79.
Peanut butter.
Thank you. And I did 82, 15 plus 6 plus 14. 20 plus 12. I thought I hit something wrong there. 57. And then these totals should of course be the same regardless of if you're going down the columns or down the rows or across the rows. 82 plus 35 plus 57. Whoops. But it might be nice to,
Double check.
yeah, 79 plus 36 plus 69. We get 184. Uh-oh.
There's an extra 10, there's 79.
Emily, there's a mistake
on
on peanut column. Yes.
Nice. 69 and 36. Okay, phew. Caught it. All right. So what we can test, so this is called a two-way table or a contingency table. So a two-way table or a contingency table. So we have these counts, and when we have these, what we're interested in is whether the distribution of the colors is independent of the distribution of the types, right? So whether these categories in each variable are independent of each other, right? This one's not as important, but well, no, it is important. But if we think about how people vote and how they respond to different survey questions, we suspect that those two things are dependent on each other, right? And so then we would do a test of independence. But this one's more fun to think about. So here, we test whether the M&M color is independent of the M&M type. The conditions stay the same, and I'm going to ignore them, but I'll mention them, but I'm not going to write them down because they're the same. But randomly sampling all these M&Ms ensures independence within the groups, but also between the groups for each variable, right? Or sorry, for each category within each variable. Now we're testing the variables against each other, right? If they're independent. So that's what we're testing. And we still have to have 5 expected counts in each cell. How are we going to find the expected counts? Well, there's a formula for that. If you were expecting all of these to be independent, then what we would do is we take, and this is just a fact, and I'll post I'll make it a little tiny video exercise because there's have you guys watched Zed's statistics? He does these really, tune in. Yeah,
Can't miss an episode.
yeah, tune in every day. That's what I thought. He does these really great, concise videos, And so it's worth checking out. And so I'm going to shove one down your throat for the test of independence, where he explains where these expected values come from. But for us, it's going to be the row total times the column total divided by the grand total makes the expected count in each cell. That's a lot of work, right? And so you'd probably want to use software for that. Unfortunately, I think Excel still makes you calculate the expected values, even though it should know what to do. And so, let's see here. What was I going to say? The null hypothesis, or let's do step 1.
We like to do this for our M&Ms or chocolates.
Yeah.
That does
And
sound
really
fun.
random data.
I mean, that does sound fun.
Don't have to do M&Ms, but like pick our own,
You're right. We should do Skittles,
something like.
M&Ms. Yeah, you know what? I think that's a fun project.
That would be interesting to.
Yeah, what else comes in different colors? Mini eggs.
Oh, mini eggs, that's good.
Oh,
Good
huh?
choice too, yes.
Hard to, well, I guess there's the mini eggs, the eggies.
Well, we have to probably pick like one type of, like M&M's work, because I think the colors are the same for a couple of different, like dark chocolate,
Yeah, right?
like I think they have the same colors, so we could do this easily. Other Skittles, probably the same, like, you know, they have different, like, chocolate flavors.
Yeah, right?
Could be different.
Okay.
But, again,
Okay. Yes.
yes, we can, maybe.
Yeah. I'll yeah. I do want to do that. I'll figure out a way to kind of yeah. Yeah, make it a little bit. Yeah. I'll incorporate it somehow.
Cool.
We'll see if Allison will buy us the M&Ms. That might be nice,
Why
huh?
make them all by
You accidentally buy a bag of Christmas M&Ms? It's all off. Yeah, yeah, or really late. For a test of independence, our hypotheses will of course be variable 1 is independent of variable 2. For our null hypothesis, we have to assume that these two groups are independent of each other until we have proof otherwise. Okay, and so generically, variable 1, and maybe I'll put a title because it's a fresh page anyways. So the chi-squared test of independence. Variable 1 is independent of variable 2. In our case, right, we said that, and it doesn't matter which one is group 1 and group 2. If we're assuming that they're independent of each other, then of course the flip side of that is they're not independent of each other, right? And so it doesn't matter. I'm going to use this as group 1 and group 2, or variable 1, variable 2, but it doesn't matter. M&M colors are independent of M&M type. Makes me think, so our M&M experiment makes me think, my husband's always, what he did in stats was they tested if double stuffed Oreos are actually double stuffed.
They're not, right?
They did find that they are not.
Yeah, they're about like 1.7 or something like that.
So could do that analysis, right? We would need to test the means, right? The average weights probably, which I'm holding off until next week to introduce, but we will be able to do that as well. So we could
Yeah, that'd be fun too.
make it
Something real world.
A
Real world.
treat themed course.
Yeah, exactly. Like, something that we can do ourselves.
So get percolating. I think another one that he was telling me about was the 2 scoops of raisin in a package of Kellogg's raisin bread. But that would be really hard to test.
Yeah.
/ annoying, really annoying. Anyways, lots of fun things. So maybe, yeah, start thinking about those. Or even what problems, right? I don't know any proportions that you might be interested in, but maybe, I don't know, some sort of, whatever you count. What are some things you count in wet?
Low. We don't-
You calculate it, right? Yeah. Do you count fish? Come on. Come on, say yes.
Sure.
Fish, frogs.
Yeah, you can count fish.
I mean, if you're doing something with fisheries, then maybe, but
Yeah.
It's the best I can do. Frogs. I don't know. Count something. Count rocks. No, I know you don't do that. Oh, okay. Yeah, because the thing about using this, right, something like this, is you are relying on counts, right? So anytime that you're counting things, then you can use usually a chi-squared is what you would end up using. Because this is the apex of hypothesis testing for categorical variables, right? And so it's as good as it's gonna get. Test of independence. Now, just as before, the alternative hypothesis is just going to be the negation of variable 1 is not independent of variable 2, and so the M&M colors are not independent of M&M type. You could say dependent instead of not independent, but I typically just say not independent just because it's easier for me to think about kind of binary situations, right? It's either independent or not independent. And so there we have our null and alternative hypotheses. The conditions are the same. I'll jot that down. Conditions are the same. You have to have independence. I said I wasn't going to write them down, but I can't help it. Random sampling ensures that that's true. And you have to have at least 5 expected counts in each cell. Well, how are we going to find these expected counts? I'm going to throw that in step 2, which is do the test. The expected count, well, first I need to define let I be the index for the rows. And J be the index, oops, for the columns. Then the expected count at IJ, right? Moving through row 1, column 1, row 1, column 2, right? We have these IJ coordinates, and I'll emphasize that there, is going to be the row total of I times the column total. Oops, of J divided by the grand total. So each one, and I'm gonna snag these. And like I was saying, I'm pretty sure, oops,
So the grand total is total.
is the 174 down at the bottom. So what this is going to look like is put this here and then. So the expected count here, E11 is 82 times 69 divided by 174. And you will get decimals and you'll want to keep those decimal places. And that's why Excel might be a nice solution here instead of doing it by hand. And so here E21 is 35 times 69 divided by 174. And just so you can see it complete-ish, 82 times 36 over 174. And that's how you're going to find your expected counts. A little bit trickier, right? Not something I expect you to do by hand at all, right? But let me just give myself one more. How much time do I have? Once you have your observed and your expected counts, right? The expected counts are assuming that you have an independent relationship, right? If your observed counts are far enough away from that, same scenario as before, then your chi-squared, how you calculate it, is the same, right? It's the sum of each observed count minus the expected count squared divided by, divided by the expected count for each cell. And then you add those all up. It's a lot of work. The chi-squared dot test, when I was looking into it the other day, it requires, so the actual counts, and you can set your table up like this, and then just highlight all of these guys, right? And then you also have to make one with the expected counts is what I was finding. Although, in my opinion, should it be able to calculate the expected counts? Yes, right? Because it knows that it should be the row totals times the column total divided by the grand total, which is all things it can find. So that's why I'm a little bit disappointed in that, I guess. But it turns out you seem to have to do it by hand, but that's okay. Pardon? Is the sum of the observed minus the expected.
Okay, okay.
Oh, that's bad, yeah. Now pressure's on. Still looks like a D.
Better though, there we go.
There you have it.
Oh. Nice. Good. And I'm not putting the subscripts on, right? It would be OIJ minus EIJ squared over EIJ, but as long as you do it for each of the cells, then you're fine. The degrees of freedom is going to be the number of columns minus 1, or let's start with the rows. Number of rows minus 1 times the number of columns minus 1. So in our case, we have 3 and 3, so 2 times 2, which is 4. 3 minus 1 times 3 minus 1. So now we have 4 degrees of freedom. So that's really, so how we find the expected counts changed a little bit just because we have more stuff. And the degrees of freedom relies on both variables, right? How many categories, right? Number of rows and number of columns. How many do you have in each variable? And then once we have our chi-squared and your degrees of freedom, then you can find the p-value, right? Just by finding the area in the tail. So then here, step 3, find the p-value. We'll use chi-squared dot dist of the chi-squared, which it uses x, and the degrees of freedom in true, oops, and the p-value is going to be always 1 minus that, right? Because this gives you the area to the left and you want the area to the right. Right. So I snuck that in there, that 1 minus. Then your conclusion stays the same as always, right? If the p-value is small enough, you have enough evidence to reject H naught, and the colors and the types are or are not independent of each other. I don't know. Step 4 is your conclusion, which stays the same as before. Whee! And with that, I release you. You have any questions, let me know. Otherwise, I'll see you on Monday. Stop this.